Hello everyone, I am Xiaojun. I am going to introduce our research on AI Trojan detection using meta-neural analysis. We know that nowadays machine learning models have been applied in different tasks, but it is not easy to train a machine learning model. Therefore, a convenient way is that we have expert model producers to train machine learning models and share it with consumers. For producers, it allows them to share the service without sharing the datasets, which may be confidential. For consumers, it saves their resources and expertise required to train a good machine learning model. But there are integrity threats in sharing the models if the model producer is untrusted. A well-known threat is the Trojan attack, where the producer will share a malicious model. This Trojan model will produce correct results on normal inputs. However, on inputs with a trigger, the model will produce malicious results. In this case, the trigger is a sticker and the model will recognize the stop sign as a speed limit sign. This attack is not only dangerous but also stealthy because the Trojan model is similar with the benign one on most inputs, so it is difficult to detect it. Previous researchers have proposed different types of Trojan attacks. These two attacks are based on poisoning attack. The modification attack will do pixel modification, and the blending attack will blend an image pattern. There are also attacks without poisoning the training set. These two attacks will generate an optimized trigger pattern. The parameter attack will fine-tune a trained model, while the latent attack will train a model from scratch. And note that these attacks originally focus on image classification tasks, but also can be adapted to other fields. We see that Trojan attacks are dangerous and stealthy, so our goal is to detect these Trojan models. Here is our setting. For the attacker, he will train a Trojan machine learning model and share it with others. We assume that he has full access to the training data and the training process, so that he can perform arbitrary attack as he wants. For the defender, we are given the model, and our goal is to determine whether it is Trojan or not. We assume that we do not know the attack approach nor the training data, and we only have black box access to the model, which means that we can only query the model and get the confidence score of the prediction. We do assume that we need a small set of clean data, which follows the same distribution of the training set of given model. This setting is also assumed in other Trojan detection. Now we will introduce our approach. Our pipeline is based on the idea of meta-neural analysis. It will train a meta-classifier over neural networks. This means that the meta-classifier will take a neural network as input and output a prediction of certain property of the input neural network. Meta-neural analysis usually consists of three steps. First, it will train a set of shadow models with and without certain property. Second, it will use the shadow models to train the meta-classifier. And finally, it uses the meta-classifier to predict the property of the target model. It is natural to apply such pipeline to detect Trojans. We also have three steps in our pipeline. First, we will generate a set of benign and Trojan shadow models. Next, we will train a meta-classifier to distinguish between benign and Trojan models. And finally, we apply the meta-classifier to the target model. In the pipeline, we have two major questions: how to generate a good set of Trojan model for training, and how to train a good meta-classifier to distinguish Trojan and benign models. We are going to introduce them in detail. In the first step, we will generate benign and Trojan shadow models. We hope that the shadow models are diverse so that the meta-classifier trained on these shadow models can generalize well. Therefore, we propose jumbo learning to generate various Trojan models. We will first sample different trigger patterns and malicious behavior. Then, we use poisoning attack to generate Trojan models. That is, we will inject the data with sampled pattern and behavior into the training set, and these are examples of the generated trigger patterns. To do the sampling, we use 4 parameters to parameterize a Trojan: the trigger mask, the pattern, the transparency, and the target malicious behavior. Here, the target malicious behavior is the desired output by the attacker. For example, in the traffic sign case, the target is the speed limit sign. In this digit case, it is a specific digit for outputs. Having the Trojan setting, we can generate the corresponding poison datasets and train the shadow models. Having the shadow models, the second step is to train a meta-classifier to distinguish between benign and Trojan models. The main problem here is how to feed the neural network as an input to meta-classifier. What we want here is actually a feature extraction function to transform the neural network into a numerical vector. Our design is to find a set of queries and use the output of the neural network as the feature vector. We will concatenate the output of the model and get a feature vector. Having this feature vector for a neural network, we will use a 2-layer neural network to determine whether the model is benign or Trojan. Note that there may be other design of feature vectors. For example, we can directly use the model parameters as the feature representation. Our intuition here to use this feature vector is that Trojan attack is characterized by its abnormal output on certain inputs, and therefore, we want to use the model outputs on some queries as its feature. So now, the key problem is, how do we choose this query set? A simple way is to randomly choose them. Then we can optimize a loss function with respect to the model parameter. However, we find a better approach and we call it query tuning. We find that we can optimize the goal with respect to both the parameters and the query set. And since the overall calculation flow is differentiable from the optimization goal to the query, we can use the same gradient descent technique to simultaneously train the model and tune the queries. This helps us to find the most useful queries for the prediction. We also propose another baseline method to train the meta-classifier. Suppose we do not want this jumbo learning strategy and only have benign shadow models. Then we want to fit the meta-classifier using only benign models. And this is the novelty detection setting, and we can apply the technique such as one-class SVM. In practice, we use a variant, the one-class neural network, as the training algorithm. Using this approach, we can train the meta-classifier using only benign shadow models. After we train the meta-classifier, we can apply it to the target model. We will feed the query set into the target model to get the feature vector. Then we use the meta-classifier to determine whether the target model is Trojan or not. We conduct the experiments on a variety of tasks, including computer vision, speech, energy data, and natural language. And we compare with many previous works in detecting Trojans. We show that our approach with jumbo learning and query tuning, that is, the pink bar, achieves the best result on most tasks for modification attack and blending attack, which is denoted by the M and the B here. The patterns in these attacks are modeled by our jumbo distribution, and we are also interested in how the model performs on the patterns that are not modeled in jumbo learning. Therefore, we designed these attacks, which is completely out of our jumbo distribution. We apply these patterns and perform the poisoning attack and use our pipeline to detect it. And we can observe here that the model still generalizes well, even if the pattern is out of the distribution. Then we consider the evaluation for unforeseen attacks. Recall that we use poisoning attack to generate the shadow models, and these are two attacks that will not poison the dataset. So we will evaluate whether the system can detect these attacks. We can see that our approach still performs very well in detecting these unforeseen attacks. Note that some other detection methods only detect the dataset level Trojans, so they cannot detect the attacks because these attacks do not interfere with the datasets. We also consider another attack goal named all-to-all attack. In previous discussion, we all use single target attack, that is, the model gives the same output on seeing the trigger pattern. While in all-to-all attack, the Trojan model will rotate its prediction when it sees the trigger pattern. For example, on an image of 0 with trigger it says 1, and on an image of trigger of 1 with trigger it says 2. We apply our system to see if it can detect Trojan models with this type of unforeseen attack goal. We see that our approach still performs well and outperforms previous works. And we also compare the time efficiency of our pipeline and previous works. Recall that we have 3 steps in our system. The first 2 steps to generate shadow models and to train the system will take a long time, but they are offline preparation because we only need to do it once for one dataset. In the online part, given a target model, we only need to feed in the queries and go through the model and the meta classifier only once. So the online detection takes only several milliseconds for one target model. As a comparison, the previous methods need to rerun their entire pipeline whenever they get a new target model, which takes at least 20 seconds. Finally, we consider the adaptive attack, that is, what will the attacker do if he knows our algorithm, and what we should do as countermeasure. We find that the attacker can intentionally bypass our detection model if he has full knowledge of our system. His success rate would be very high if we do nothing. Therefore, we would like to propose a robust version against the adaptive attack. Our intuition is to incorporate randomness in the algorithm because the attacker cannot control randomness. So in our robust version, we will use a randomly sampled meta classifier and keep it unchanged. Then we only fine-tune the query set with respect to the random classifier. Finally, we will use the fine-tuned query set together with the random classifier to detect the Trojans. Since the attacker cannot know the random meta classifier, it will be hard for him to perform the adaptive attack. Here is the result of the adaptive attack. The blue bars are the robust result before attack, while the orange bars are after the attack. We can see that the attacker can still manage to reduce the chance of being detected, but the margin is smaller now. That's all for our project. Here are the takeaway points. First, we show that metaneural analysis achieves a good performance in the detection of Trojan machine learning models. In addition, such system is very efficient at the inference stage. Finally, we propose a robust version of our system, which can detect Trojans even if the attacker knows our detection algorithm. For more details, you can check our paper and open source code here. Thanks for listening.